Hi, welcome back to my channel. As you can see that I have a brand new board. In fact, this is a new place, a new spot, new lights. Everything is new for me, but I have tried not to make any changes to the green board theme kind of classes that I usually take, because I know how much you guys love that feeling of classroom kind of lectures. So same theme, new place, new board. So let us start. In today's lecture, I want to talk about a very important topic in special theory of relativity, which is the space-time interval, also known as the invariant space-time interval. You see, one of the consequences of the postulates of relativity is that two observers can never agree upon the time periods and distances measured by them anymore. This is the length contraction or the time dilation phenomena. So let's suppose that you have two different observers. Let's suppose one is an observer at rest with respect to the ground. I'm going to call this observer at rest. And there is another observer, I'm going to draw it with orange color. He is a moving observer compared to the observer in rest. So this is a moving observer. So he is in a car or a train or a spaceship, whatever it is. The orange observer is in relative motion with respect to the observer in the ground, which is at rest. Now, if both of them measure the length of, let's suppose, some object. Let's suppose they measure the length of a scale. Okay, so if I have a scale here, and the scale has endpoints A and B. Now, if the observer in rest or the observer in ground measures the length of the scale, and he ends up measuring a length of del L, and the observer which is in motion measures the length of the same scale, he measures the length to be, let's suppose, del L dash, or I'm going to call it del L bar. Okay, bar means moving frame, with respect to the moving frame. According to the postulates of special theory of relativity, these quantities are not equal. The distances between the same points as measured by two different observers are not the same anymore, according to special theory of relativity. Similarly, if there are two events that takes place, let's suppose these events are, I'm going to call these events just some kind of an explosion somewhere, let's suppose, explosion A, and I'm going to call this as explosion B, that happens at different locations and different time periods. So according to the observer at rest, the time period difference between these two events, if it is, let's suppose, del T, and according to the moving observer, if the time period difference between these two events is del T bar or del T dash, we know in special theory of relativity that these two quantities are not equal. The first is related by what is known as the Lorentz Transformation or the length contraction here. The second is the time dilation. So two observers can never agree upon the distances between space or distances between points in space and the time periods between physical events. So space and time, or measurements of space and measurements of time, are not absolute anymore. They are relative. They are relative to the relative velocity of these observers, and they are given by the length contraction formula and the time dilation formula. So isn't this some sort of a tragedy? Because we live in a world in which we have a feeling that the distance between 2 points as measured by me and somebody in motion must be the same, but that is gone, poof, vanished in thin air. We live with a certain kind of commonsensical idea that the rate at which time flows must be the same for me as for another observer, but no, that's also gone, poof, vanish. Gone are those days. So in modern physics, and this is very much apparent only when relative velocities are very, very high, of course, but as a physical rule, as a physical principle, the distances between any 2 points and the distances and the time periods between any two physical events are not the same for two different observers in relative motion. So, can we obtain something out of this? Is there something that we can hold on to? Is there some quantity that is actually same for both the observers? Is there a quantity that both the observers can agree upon? Is there some quantity that an observer in rest and an observer in motion can agree upon, that their measurements are the same? Because they cannot agree upon distances, they cannot agree upon time periods, but there is a quantity that they do agree upon when measured for the same events, and that quantity is known as the space-time interval. So a physical quantity which is the same for an observer in rest and an observer in motion for the given set of physical events is known as invariant. Invariant means it does not change. Under a Lorentz transformation, it does not change. So when we connect the measurements of an observer in rest and observer in motion, we connect those measurements via what is known as the Lorentz transformations. So Lorentz transformations are the transformation rules based on which we can connect the measurements of two different inertial observers in relative motion. And under a Lorentz transformation, there is a quantity that both of them agree upon that does not change, that is invariant, and that is known as the space-time interval. So in this video, I'm going to talk about the space-time interval. First, I'm going to prove that it is indeed invariant under a Lorentz transformation between two frames of reference. I'm going to prove that. Second, I'm going to talk about the physical significance of that kind of an interval. What does it tell us? Well, it tells us something more than just one physical quantity that is invariant. Of course, in this kind of a world where observers cannot agree upon time periods and lengths, if we do have a quantity that they do agree upon, then that quantity has some significance, yes? But it is much more than that, because it will give us an idea about how to construct space-time, as I'm going to discuss in my next lecture. We have a space, a three-dimensional space. If we want to construct a four-dimensional space-time, then this space-time interval is going to give us an idea about the properties of the geometry of that space-time. And I'm going to reserve that discussion for my next lecture. So I'm going to talk about the physical significance, and lastly, I'm going to talk about the classification of various intervals between events known as Timelike, Spacelike, and Lightlike events. So let us start. What is this interval? Well, let me go ahead and give it to you. So the space-time interval, I'm just going to straight away introduce to you, has this form, del x square plus del y square plus del z square minus c square del t square. Okay, first of all, we are dealing with physical events in three-dimensional space and one time coordinate. So everything that happens in our physical universe has four coordinates associated with it. The coordinates of space, x, y, z, and the coordinate of time. Now, if I want to look at intervals in space and intervals in time, so let's suppose I have two physical events happening, one happening here, another happening here, then there is a distance between them that in three-dimensional space can be written as del x square plus del y square plus del z square, but they may happen at different time periods, so there is also time period associated with it, so the last term is associated with the time period between those two physical events. Now, in certain situations, you may see an expression that looks like x square plus y square plus z square minus c square t square, which is kind of a simplification when you measure the interval of one particular point in 4D space from the origin of the coordinate system. But right now I am writing a general sort of an expression, so the del is here to signify that it's an interval, it's a distance or a difference between two coordinates in space-time. Now, in certain books, you may see a little bit of a difference in convention. So for example, in certain books, you can have plus sign before the time coordinate and minus sign before the space coordinates. That is also one of the conventions used. So there are two conventions. One is the plus sign used before the time and the minus sign used before the space coordinates. And the other convention which I am using is the minus sign before the time coordinate and the plus sign before the space coordinate. So both these two conventions are quite common in physics, and you may see these two conventions in different books. It doesn't matter, both of them are equally valid, and as long as you are consistent, So your calculations are going to give you the correct results. Me, in my series of lectures, in the coming lectures in which I'm going to discuss Minkowski, space-time, geometry, 4 vectors, I'll be using this convention where I use the plus sign before the space coordinates and the minus sign before the time coordinates. So this quantity, del x square plus del y square plus del z square minus c square del t square, is a very important quantity. It is known as the space-time interval, and it is invariant under a Lorentz transformation. What does it mean, invariant? It means that if there are 2 physical events, A and B, and this quantity is measured by an observer at rest, and moving observer also measures this quantity, but his x, y, z coordinates may be different. So he may say that his quantities are in fact del x bar square plus del y bar square plus del z bar square minus c square del t bar square. The bar here is to signify that the measurements are made by the moving observer. So in my previous lectures, I used the x dash symbol, y dash, z dash, but in my coming lectures I'm going to be discussing 4 vectors. Therefore, instead of the x dash, y dash, z dash, I'm going to be writing x bar, y bar, z bar, because it's sort of just helpful in terms of writing the terms, because I'm going to be dealing with superscripts a lot. So the dash and the superscript, it creates a confusing sort of an expression. So I'm going to be using the bar here. All right. So this quantity as measured by an observer in rest, and the second quantity as measured by an observer in motion. Now, they may have different measurements of coordinates. Their del x's may be different, their del y may be different, their del z may be different. The del x square plus del y square plus del z square may be different, the time periods may be different, but the overall quantity for both the 2 observers are going to be exactly the same. So they are going to be exactly equal. This is what I'm going to prove. The measurements of the rest observer and the measurements of the moving observer for this particular quantity are going to be exactly the same for the given physical events, let's suppose A and B. And that is why the space-time interval becomes so important. So before I discuss further the significance of this space-time interval, let me first prove to you that it is indeed invariant under a Lorentz transformation. So I have discussed the Lorentz transformation in my previous videos. The Lorentz transformations is simply a set of transformation equations connecting the measurements of the coordinates between 2 different observers in relative motion, 2 different inertial observers in relative motion. And quite specifically, they look something like this. You have x bar, I'm going to call it x bar instead of x dash, means the same thing, is equal to gamma x minus vt. Okay, now this is for individual coordinates. What if I want to measure the intervals between different coordinates? Let's suppose 2 physical events are happening, A and B. So xb minus xa will represent del x. How is del x related to del x bar? Well, if you create a set of equations for physical event A and another set of equations for physical event B and subtract them, you will get simply del x bar is equal to gamma del x minus v del t. Quite simple. That's it. Similarly, you will also get equations like del y bar is equal to del y. You will get equations like del z bar is equal to del z, and you will get equations like del t bar is equal to gamma del t minus v upon c square del x. Of course, you know what gamma is. Gamma is nothing but 1 upon root over 1 minus v square upon c square. So these are the Lorentz transformation corresponding to intervals in x, y, z and t axis for 2 physical events, let's suppose A and B. Again, I want to specify that the bar and the dash that I wrote in my previous lectures are actually the same thing. Sometimes you write the bar and sometimes you write the dash, but they signify the measurements being made by some S bar frame, and the right hand side x, y, z, t signify the measurements being made by some S frame of reference. So let's look at this particular quantity, which is the RHS. Okay, so let's look at what I'm going to call as the RHS. Okay, so what is the RHS here? So RHS is nothing but you have the del x bar, okay, del x bar square plus del y bar square plus del z bar square minus c square del t bar square, the del z bar here. Now, if I use the Lorentz transformations to sort of simplify them, what I'm going to do is I'm just going to use these equations. Okay, let's use equation number 1 in del x bar. So if I use equation number 1, this simply becomes gamma square, and then I have del x minus v del t square. Okay, the first. Del y bar is equal to del y, so this is nothing but del y square. Del z bar is equal to del z, so this is just del z square, and del t bar is equal to this quantity, so I'm going to write this as c square gamma square, or minus sign is here, so minus c square gamma square, so you have del t minus v upon c square del x whole square. Okay, so let us simplify this expression. Now, if I simplify this expression, what is gamma? Gamma is nothing but 1 upon root over 1 minus v square upon c square. Gamma square is the, the square root will get removed. In the denominator, you have 1 minus v square upon c square. That can be simplified to write c square upon c square minus v square. Okay, gamma square is nothing but, in the denominator, you have c square minus v square, and in the numerator, you will get a c square. Okay, and here inside the brackets, you will have del x square minus, or rather v square del t square minus 2 del x v del t. All right, fine till now. Let us look at the other terms. So plus del y square plus del z square, and the last term I can simplify as minus. So there is a c square, so c square, and then you'll have c square upon c square minus v square, which simply becomes del t square plus v square del x square, and divided by c to the power 4 minus twice del t v upon c square del x. Okay, now we want to simplify it, so we want to cancel some of these terms out. Okay, how do we cancel some of these terms out? Well, I have to bring all of them together. So let's take c square upon c square minus v square as a common. So if I take c square upon c square minus v square as a common, then in the first I get these expressions, which is del x square plus v square del t square minus 2 del x v del t. And then for the later expression, there's a negative term, negative c square. All right, so there's a negative c square here, so I need to add negative c square to all of these terms. So the first term becomes negative c square del t square. The second, this one becomes negative v square del x square upon c square, and finally I get negative, and negative becomes plus, the c square vanishes, and we'll get 2 del t v del x. Okay, and the remaining are, so this is a square bracket, and the remaining are plus del y square plus del z square. Now here you can see that some of the terms will get cancelled out. Which are those terms? So 2 del x v del t negative, and 2 del x v del t, this term will get cancelled out. All right, and let us simplify the remaining 4 terms inside the bracket. If I do that, this simply becomes c square upon c square minus v square. Okay, here let me take del x square upon c square as a common. Okay, so if I take del x square upon c square as a common, so here I should get c square, and here I should get minus v square. Okay, and for this and this term, if I take minus del t square, okay, let's suppose I take del t square, then I should get c square minus v square as a common. Okay, and the remaining are del y square and del z square. All right, and we're almost done. Just hang on a minute, we are almost done. So at least we're done for the proof. Okay, so c square minus v square, this multiplied by, here we have c square minus v square is one of the terms, and the other term is x square. So I can take the 1 upon c square term out. I can have 1 upon c square, and then you will have del x square minus c square del t square. Okay, so here again this term gets cancelled, c square and c square gets cancelled, and of course the remaining terms are del y square plus del z square. So finally we come up with our expression del x square plus del y square plus del z square minus c square del t square, which is the same expression as what we started with, but with respect to the rest frame of reference, with respect to the S frame of reference. So I'm going to call this, so this is the LHS. Okay, you see this? This is the LHS. So this is the space-time interval del x square plus del y square plus del z square minus c square del t square with respect to an observer in the rest frame of reference, and this is the space-time interval del x bar square plus del y bar square plus del z bar square minus c square del t bar square, which is the space-time interval with respect to the moving observer when they're making measurements for the same two physical events, and they are exactly equal to each other, right? That means the space-time interval is invariant under a Lorentz transformation, because we use the Lorentz transformations to get this proof. So even though both the observers do not agree upon the distances that they measure in space, right? Even though both the observers do not agree upon the time periods that they measure between physical events, they do agree upon this particular quantity. So this quantity is the same for both the observers. So therefore, this is a very, very important quantity in special theory of relativity, because it is invariant under a Lorentz transformation. That means two different observers in relative motion will agree upon their measurements when connected via the space-time interval. So that is the space-time interval, which is a very, very important physical quantity because it is invariant under a Lorentz transformation. It is invariant when we go from one frame of reference to another. Now, in some situations, instead of writing the del x, they will write x square, which simply means that the interval is measured between some point and the origin. Here I have written a more general sort of an expression between two individual points, let's suppose A and B. Okay, so you understand what del x is. So del x is nothing but let's suppose xb minus xa. Okay, del x is nothing but xb minus xa. So the x component as measured by the rest. What is del x bar mean? So del x bar simply means that x b bar minus x a bar. That means the x component or x bar component differences with respect to the moving observer. Similarly for the other quantities. So I hope you understand the definitions that are involved. Now the question is, what is the importance or what is the physical significance of this particular interval? Now of course, we don't even need to go there. Finally, we have come up with some quantity that is consistent across the various inertial frames of reference. Lengths and time periods are not consistent, but there is a quantity that is consistent across various inertial frames of reference. So that itself makes it very, very important. But there is something more than this. We can get some idea about the geometry or the properties of space-time. You see, now we cannot deal with coordinate systems that just contain space, x, y, z. Now we need to create a coordinate system that also involves time. So we need to create space-time, and this new space-time and the geometry and the properties associated with the space-time will be revealed by the nature of this particular quantity. I will not go too much in detail, but let me just give you a taste of it, okay? Okay, so I have written it a little bit in detailed fashion just so that there is clarity. So for a rest observer and a moving observer, if there are two physical events and the coordinates of the physical events for the rest observer are these and the coordinates of the physical events for the moving observer are these, then the space-time interval for the rest observer and the space-time interval for the moving observer are exactly equal. If I write it in a little bit detailed fashion in terms of the coordinates, so del x is nothing but xb minus xa. Similarly, del x bar is nothing but x bar b minus ax a bar. So this is just written in a detailed fashion just so that there is clarity. Now, let us come to the question, what is the significance of the space-time interval in terms of the geometry of space-time? You see, earlier we had coordinates which only consisted of space. So for example, just to give you an illustration, we usually deal with motion of particles in 3D space. Yes, so if we talk about 3D space, so one of the most common coordinate systems that we use is the Cartesian coordinate system. So here we have x, y and z axis. So if we are trying to find the interval between any 2 points, let's suppose we have point A and point B, then the interval between any 2 points in space is given by, the usual del x square plus del y square plus del z square. However, now we need to construct a space-time which includes not only the 3 space directions or the spatial directions but also a time direction. Now it is not easy to visualize a 4D space-time in 3D space. It is not easy, in fact not possible to visualize a 4D space-time in 3D space. So I'm not going to draw the diagram. I don't know how to draw a 4D space-time, but this interval means the same thing. So just like this quantity is nothing but the distance between 2 points A and B in 3D space, the space-time interval is in fact the distance, square of the distance between any 2 points in 4D space-time. So instead of 3D space, if we have 4D space-time, so this is in fact not the distance, okay? This is the square of the distance between any 2 points. Similarly, the square of the distance between any 2 points in 4D space-time is in fact the space-time interval, which is del x square plus del y square plus del z square minus c square del t square. Now, how does that tell us anything about the nature of space-time? To understand, we need to reduce the number of spatial directions. Okay, so let's suppose that there's a body which is constrained in one dimension. So it's only able to move in the x-axis. So let's remove the y and z axis. So let's just construct a 2D space-time, okay? 2D space-time, let's construct a 2D space-time consisting of x, all right, the coordinate x and the coordinate time, and we will call that as ct because ct is the term that is appearing there. And let's suppose that I construct this 2D space-time in which there is a y-axis and then there is the x-axis. So y-axis is nothing but the time axis. So this is the ct axis and the x-axis is the usual x-axis. Now, the space-time interval is in fact the square of the distance or the interval between any 2 points in space-time. So let's suppose that I have some kind of a point A and another point B. I want to measure the distance between these 2 points. Let's suppose I call it A and I call it B. Then this square of the distance is nothing but del x square. Now y and z are not present. Let's suppose they are all 0. So this is nothing but c square del t square. If I remove y and z, the space-time interval takes this particular form. Okay. So what does this mean? This means that the distances in the del x axis, so this is del x basically, okay, this is del x, okay, and the distances in the time axis, so this is the time axis, so this is c del t basically. So this distance, what I'm going to call as, let's suppose I call it s, okay, let's call it del s, okay. So del s square is equal to del x square plus c square del t square. Now, if you are following this discussion, you might have got something peculiar. What is the peculiar thing happening here? the square of the distance between points A and B in the space-time, 2D space-time, is equal to del x square minus c square del t square, right? This is the interval that I am saying is actually the interval in space-time, okay? This is the interval that I am talking about, right? But now you would say, but sir, wait a minute. Isn't this a right angle triangle? Shouldn't this follow the Pythagoras theorem? Shouldn't this be del x square plus c square t square? Because that's what the Pythagoras theorem is. Well, now this is where, a new world begins, because space-time is not your usual Euclidean geometry. We live in a Euclidean geometry where Pythagoras theorem is followed essentially. So in 3D space or 2D space, if you construct any kind of a line, you can decompose their, x-axis and y-axis, and then you can construct the magnitude square to be del x square plus del y square. That's a Pythagorean theorem, right? But in space-time, the geometry of the space-time is peculiar in the manner that it does not follow the Pythagoras theorem. It does not follow the Pythagoras theorem, and we will discuss this in the next lecture when we talk about space-time a little bit in detail, because how Euclidean geometry is different from the space-time Minkowski geometry. We will discuss that in detail, but this is just a taste of what I talked about, that the space-time interval, which represents the distance between any 2 points in space-time, is equal to del x square minus c square del t square. And this hints at the possibility of a certain geometry in space-time which is not the same as that of 3D Euclidean space. Alright, so I'll keep the discussion of this physical significance and the geometry of space-time and how it is different from Euclidean space here. I'll discuss it further in the next lecture, but I want to finish today's lecture with a few more classifications. So if you study space-time interval of various physical events, so they can be classified in 3 different categories. So if you look at this particular quantity, it can have 3 distinct values. It can have a positive value, it can have a negative value, it can have a 0 value. And various intervals are classified according to whether they have 0, positive or negative value. So let us look at that classification. Okay, so let us discuss the Timelike, Spacelike and Lightlike intervals. So this is the space-time interval, del x square plus del y square plus del z square minus c square del t square, right? Now, because del x square, del y square and del z square represent the distance in space, so therefore I have written that as one quantity, del r square. So it represents the distance or the square of the distance in space. Now this quantity del s square can have a positive value, negative value or 0 value. Alright, based on that we can have 3 different classifications. So del r square represents the spatial distance or the square of the spatial distance between any 2 points, and del t square represents the square of the time period basically. Alright, so first condition is that, let's suppose if you have del s square is less than equal to 0. Alright, so in this kind of a situation, if del s square is less than equal to 0, you will come up with a situation where del r square is minus c square del t square is less than equal to 0, which leads to the conclusion that del r square is less than c square del t square. So these are 2 physical events such that the spatial distance square is always less than c square del t square. Alright, now what does this mean? It means that if we observe these physical events from various frames of reference, the magnitude may change. The del r square may increase or decrease, the del t square may increase or decrease, but their inequality will remain valid. That means del r square will always be greater than del t square c square, right? So that means for these physical events, we can always find some specific inertial frame of reference where del t is never 0. Because if del t becomes 0, then 0 has to be greater than a positive number, which is not possible. So it's never going to happen that we're never going to find some sort of an inertial frame of reference where del t is 0. In fact, we can always find some frame of reference where del r is equal to 0, alright, and del t is somewhat positive. This possibility is there, but the reverse possibility is not there. That means we can find, out of all possible inertial frames of reference, we can find one inertial frame of reference in which the physical events are separated in time but not separated in space. They are not separated in space, they are separated in time. That's why these are known as time-like intervals. So out of all possible inertial frames of reference for these physical events, we can find some inertial frame of reference where the physical events are separated in time but not separated in space. They are known as time-like intervals. Similarly, we can have a second condition where del S square is greater than 0, which simply means that del R square minus C square del T square has to be greater than 0, which simply means that del R square has to be greater than C square del T square. Now, of course, these are for different physical events and these are for different physical events. So, for these physical events where del S square is greater than or equal to 0, we can always find some inertial frame of reference where del T is 0, but del R is never 0. Because if del R becomes 0, it simply means that 0 has to be greater than some positive number, which is not possible. So for these physical events where del S square is greater than 0 or the space-time interval is greater than 0, we can always find some inertial frame of reference such that the time interval comes out to be 0, but the spatial interval is never 0. It simply means that the physical events are separated in space but not separated in time. So for those space-time intervals where we can find one inertial frame of reference where the physical events are separated in space but not separated in time, these kind of physical events are known as space-like physical events or space-like intervals. And finally, we have the last condition where del S square is equal to 0. It simply means that if del R square minus C square del T square is equal to 0, then del R square is equal to C square del T square. That means the physical event is happening in such a manner, or the physical events are happening in such a manner that the spatial distance and the time distance or the time differences are connected by the speed of light. That means two physical events are happening at two different locations and time periods such that they are connected by a light photon going from one to another. That means if one physical event happens at one point in time, if a light photon goes towards the other physical event, by the time the light photon reaches that point, the other physical event is going to happen. So the spatial distances and time periods are connected by the speed of light, and these are known as light-like intervals. So that is all. In today's lecture, we have discussed what is space-time interval. It is an interval in 4-dimensional space-time between any 2 points or any 2 coordinates, and the magnitude or the square of the magnitude of those 2 points or the interval itself is something that all observers agree upon. It's invariant under a Lorentz transformation. Then we discussed the physical significance of this kind of a space-time interval, and then we discussed the classification of various kinds of intervals as time-like, space-like, and light-like. I'm going to continue this discussion further, and I'm going to elaborate on many of the things that I've touched upon today in my next lecture. So I'll see you then. Have a nice day. Bye-bye.